We are now live.
Hey. Hello, everyone. I want to thank you for coming in today. We're going to have both Astrolabe Analytics and Smart Drive presenting today. Astrolabe has some really good technology on the, sorry about that, I got to mute some video here, or some audio. But Astrolabe has some great technology, great solutions for managing batteries and battery life. Also, you can work on monitoring your batteries and make it or optimize your ordering, your storage, your usage. And then the smart dry was an interesting technology that I believe has many more applications than what they are going to present on. The liquefaction is, I think, something that would apply in several areas. I'd like to hear some feedback as we go on as to where you think that could apply in your industry. I mean, beyond mining, and look at things like possibly cleaning up soil and environmental applications as well. So with that, I would like to go ahead and turn it over to Robert Massey from Astrolabe. Robert?
All right, sounds good. Let me share my and all right, can you see my screen?
Yes, I can.
Okay, great. So let me know if anything goes sideways, but hopefully we'll be off to the races from here. So yeah, thanks for the opportunity to speak today. I'm the founder and CEO of Astrolabe Analytics. We are an early stage battery analytics startup looking at different applications across wherever you're putting a battery, drones, UAVs, electric aircraft, stationary storage, just about any place where you're putting a battery into some scenario. We are happy to help optimize that lifetime and performance using our analytics. So let me see if I can advance. There we go. So, right, just a quick and dirty overview here. We've been around since 2018. A couple $1 million worth of projects through SBIRs and other things of that nature through the Air Force and National Science Foundation. And basically, like I said, looking at different ways to help optimize the use and performance of battery-powered assets across defense and aerospace in particular. But like I said, anywhere where there's a battery, we can be making ourselves useful in one way, shape, or form. So we are a team of battery and data science folks out of the University of Washington. I did my PhD here in Seattle, and I've been working on Astrolabe full time since I finished that about 2 years ago. And yeah, I've been putting together the rest of the team to help out on the doing the heavy lifting on the data science side, on the product development side, all the other pieces of the puzzle to commercialize our technology and move things forward more or less. So, right. So, as I mentioned, we're looking at different things across defense, aerospace, automotive. All these things are becoming electrified as the cost and performance, as the cost of batteries goes down and the performance of batteries goes up. But there's still a lot of unsolved questions when it comes to how a battery is going to perform in different scenarios. The battery that goes in Tesla is going to behave differently from a battery that goes into a forklift or a pacemaker or all these other things. And there's a lot of best practices that have still yet to be developed for these different applications. So this is a problem for the folks who need to operate and maintain these systems. You could be putting a battery into service that is, a hazard to whoever is operating that aircraft or forklift or whatever that battery is going into. And on the other hand, if you're, too conservative with retiring your batteries. That's a to avoid the catastrophic failures. Now all of a sudden you've got um, you're over investing in inventory that could probably be used and extend the life of these batteries. But now you're just adding additional maintenance hours and cost on the back end that way. So it's a difficult balancing act that folks are trying to come up with different solutions for. So that's where we come in. We're able to help folks who are developing or operating or maintaining their batteries, um, helping them to get the most out of these batteries with condition-based maintenance type of approach. So this is a combination of software and services that we offer. At our current stage, we've got a product that we're working on in the background, and then providing different services around proof of concept or consulting to just pay the bills and keep the lights on as an early stage startup. But yeah, the main idea here is we'll take your battery data and use that to help you reduce the cost of maintaining and replacing these batteries, ensure high system safety and uptime, and prevent mission failure in defense and aviation type applications, among others. So,
Robert,
yes.
Eugene. So now, are you working with individuals as well, or is this more for large companies and small businesses, universities, that kind of thing?
Yeah, we're B2B, so our customers are folks who are, it's not like the people who are, it's not the battery OEMs per se, it's more like people who are integrating the batteries into some product that they are in turn delivering to a customer. So it could be stationary energy storage systems, could be, like I said, people who are manufacturing forklifts or drones or robotics or electric aircraft are a couple of different use cases that we've worked on. Just about anything except automotive. We haven't worked with Tesla or Ford or any of those folks yet. Um, Anywhere in the across the value chain of the batteries. Does that make sense?
All right. Yeah. So then if my company maintained a fleet of quadcopters or something, you would be able to help us, even though we didn't manufacture them.
Right, right. Yeah, we would, depending on the application, it would be the type of thing where we would integrate into the whatever fleet management software or energy management system software. We'll get into some of the more specific applications as we go, but it's the type of thing that could go either in on the hardware itself on the BMS and or in the cloud, depending on what is appropriate for a given situation.
Okay, I'll let you go on. Thank you.
Yeah, so just to hit the value proposition a little bit more, we're basically looking at reducing the operating cost and ensuring safety and uptime for these types of systems. So on the one hand side, that's the maintenance component. There is a couple irons in the fire that we're basically proposing to a DoD outfit that will be able to reduce their estimated cost of batteries by 400K per year by extending the lifetime of these batteries. So right now, well, oftentimes happens is the battery is you basically put like a timer on it and you retire the battery after X number of years, regardless of whether or not the battery is still good or not. By integrating our analytics, we're cautiously optimistic that we can double that, so thereby extending the life of these batteries and reducing the number of batteries you need to buy. So that's one hand on the maintenance side. And yeah, on the operations side, just giving the operators real-time insights into what the battery state is, state of health, state of charge, state of power, that sort of thing, so that the batteries are always ready to go for a given application. So how we do that, we'll basically take your data, run that through our various algorithms, and provide you with the information to say, okay, is this battery safe? Do we have any warranty issues we need to worry about? When should we be servicing the battery? Those types of questions. So like I said, this could be going either in the cloud and or embedded on the battery hardware itself, depending on what is appropriate for a given situation. So yeah, these are a combination of different algorithms, both data-driven and inspired by my PhD work at the University of Washington looking at battery electrochemistry. So So, yeah, the types of folks, kind of to your previous question, Eugene, the folks that we're looking at working with, if there's a specific mission and or business need where you really need to understand what that battery is doing, if we can either help you save money and or ensure system readiness, that's the type of thing we're looking for. We also like to have historical data and or some kind of telemetry where we can get access to the data in real time in order to put together a proof of concept and or embed these algorithms in the real world on real hardware. So a couple different applications, like I said, eVTOL, that's electric vertical takeoff and landing. We've got a previously won a phase 2 SBIR with the Air Force, looking at how we would take our analytics and use that to help ensure the safety of electric aircraft. So that's a novel application where it's really one of the most demanding things you can try to do with a battery, make the, make an aircraft fly vertically up in the air, then fly for, X number of miles and then land safely again. So a lot of different companies are working on that, and we're happy to help accelerate that electrification of flight. And then, like I mentioned, UAVs, obvious defense applications there. If you've got swarms of drones or either a large number and or high value UAVs, you want to make sure that they are not going to, when you send them out, you want to make sure they're coming back for certain applications. But another application where understanding battery health and performance is important. Likewise for energy storage systems, stationary storage is easier because the battery just has to sit there. But you still want to understand, okay, if we're pushing the battery hard today, how does that impact the long-term health of the battery in the future? Those types of questions. So the thing about batteries is it's always trade-offs whenever you do one thing. If you make one thing better, you're probably making something else worse. And you just need to be making rational decisions about how you're optimizing and using these batteries. So our business model at our current stage, it's a combination of services and software. Customer engagement usually begins with some sort of proof of concept, so some kind of pilot project. You give us your historical data or lab data or field data. We'll run our algorithms, run that through our algorithms in order to look at a specific problem in question. So whether that is building a better state of charge estimator or doing a post-mortem on why some batteries were failing prematurely, different things like that. That could be a starting point. And if we do a good job on the front end, we like to have long-term relationships with some of our customers moving forward from there. That's where we would be, taking the proof of concept algorithms and embedding that onto the BMS, into fleet management software, whatever the software that is controlling these assets. There's different things for different market segments, but more or less the idea there being actively monitoring batteries to make sure that they are doing the thing they're supposed to be doing. So, like I mentioned, a couple different applications, electric aviation. We've got a product coming out hopefully at South by Southwest that I'm excited to talk about more once we have that ready for prime time. So that'll be coming up in March. We've got an active phase 2 SBIR with NSF looking at stationary storage applications. Like I mentioned, we've got the previous and in the works SBIRs with the Air Force looking at drones, electric aircraft, things of that nature. And just across the board, where we've got a battery in a system where you care about its long-term health and performance, we're happy to help best maintain those systems and provide guidance for getting the most out of those batteries. So I will pause briefly here for questions. Here is where, as a break, I can go into arbitrary depth on some of these applications, depending on what level of detail folks are interested in. Yeah, I'll just take a quick break for questions here before moving forward.
Why don't you go ahead and move forward?
All right. Well, in that case,
yeah, because we're not live interactive yet.
Gotcha.
So that's going to be next week.
Yeah, no worries there. If there's any questions in the chat or something like that, let me know. kind of flying blind a little bit, but
Yeah, I know. I
all right, cool. So I'll just run through some of these applications and case studies, and let me know how we're doing for time, Eugene, if we get close there. So, um, like I
will do.
mentioned, electric aviation is one of the use cases that a whole bunch of folks are interested in, including the Air Force. Moving troops and materiel around is an important, part of the job there. And electric aircraft promise to deliver, cost savings for reduced total cost of ownership and increased operational mobility if we're able to bring this technology forward. And like I mentioned, electric aircraft is one of the most demanding things you try to do with a battery is for eVTOL when you're taking off and then landing. It takes a lot of power. It's like depending on some of the designs, it's like a megawatt of power for 30 seconds at the beginning and end of uh, uh, the takeoff and then landing phases of these flights. Um, During the takeoff, you've got the battery is at a higher state of charge, so you've got a higher voltage, so you don't need quite as much current to get the same amount of power. Versus the tricky part is really when you're at that landing stage, you're now at a lower voltage, and you have to compensate by having an even higher current to get the power required to perform that maneuver. So, especially the landing phase, what you need to be designing these batteries around. Um, in order to make sure that you've got the right power and you're not going to, literally fall out of the sky and have bad things happen. Unlike electric cars, you don't have the luxury of pulling over to the side of the road if something goes sideways. So you really need to just have like extra level of safety and performance for these types of applications, which are still, TBD under development with the FAA and other regulatory bodies there. But yeah, like I mentioned, this is kind of a quick snapshot of the output from our phase 2 SBIR with AFWERX. On the left-hand side, you've got either the cell and or flight data from these battery systems. We run that through our algorithms. So all these different gray boxes represent different algorithms for estimating the state of the battery, more or less. Then on the right-hand side, that is the output that is either going to the operator who needs to know, real-time information about how much time they've got left before the battery is going to run out of juice, and or information that goes to the maintainers who need to know about how the battery is aging and different things of that nature. So combination of different things there.
So, Robert,
Yes.
really quick here. So when you mentioned before about the lithium ion batteries in vehicles, the so with flooding and stuff like that and the possibility of the batteries exploding, is there anything that you can do with that regard, either to prevent that, I guess you couldn't prevent it from exploding if it's shorted, but over temperature and stuff like that?
Yeah. So I guess what I would say there is we don't necessarily have a solution for it today. We're analytics, so we're not going to be able to put out a fire if it starts. But the idea there would be we can give you an early warning that batteries are going to fail, and you kind of bucket it into the battery is aging on a trajectory with usage, or the battery is aging faster than expected. So maybe there's something something is uh, this battery is either got something wrong with it or it's approaching end of life. And this is all pending a separate SBIR that we're looking at putting together for NSF, proposing some of these methods for detecting this in as far in advance as possible. So if the battery is going to explode, then it's still unknown. For example, there's all these bike fires, e-bike fires that you might be hearing about in places like New York. That's one of the things that we're looking at putting together a proposal around is understanding how far in advance in the data can we see these batteries as they're failing. Is it like a sudden onset, like if you're doing something wrong with the battery and you're charging it and all of a sudden something goes wrong with the charger? Is it like seconds or minutes, or can we see in advance how these batteries are aging and provide advanced warning to the users far in advance? So that's one of those open questions that people don't have an answer for yet, or at least if they do, I don't know what the answer is. Um, but yeah, that's one of those things that's kind of an open question for the industry that we are exploring, for example.
All right,
So I guess
so you do the analytics, but would you provide the sensors or the ability for a Bluetooth connection to a phone, let's say, that could warn somebody?
right. So I guess that would
Or
be
would that
in
be a partner provider that would have to do that?
yeah, that would depend on how we integrate into a given, product. If that was like, for example, the e-bikes, um, yeah, our core competency would be the analytics, but we could either provide that as an additional, component of the product and or integrate into some other solution that is already doing something like that. So, so like I mentioned previously, we're not trying to be all things for all folks, but we're trying to, get really good at the predictive analytics piece and then, figure out the right partners that we can integrate with, whether that is, the fleet management for drones or energy management systems for stationary storage or, some of these other apps that we could integrate with for the, e-bikes, things of that nature. Um, yeah, I don't necessarily want to spin up an entire hardware and software solution for all of that ourselves. We're happy to integrate into whatever is already existing as need be. Uh, we can, if need be, depending on different folks have different levels of technical maturity that we see with respect to their battery product development and all that. So sometimes we end up you know spinning up some basic infrastructure for them as far as battery data management and data hygiene, that sort of thing is concerned. But yeah, broadly speaking, we don't provide any additional hardware today. Maybe as we grow and uh, uh, get different pulls from the market, then we'll evaluate that on a case by case basis. But our bread and butter is basically the algorithm development and uh, mapping the right solution to a given business problem, more or less.
Okay, but you're not shying away from partnering if someone wants to
Right.
access your analytics.
Right. Yeah, we're definitely happy to, integrate it into either an existing system or, uh, developing different APIs, whatever makes sense for a given application. Yeah,
All
we're
right,
happy to we're happy to be that, that extra piece of the puzzle that maybe you've already developed 85% of the solution, but we can help add that additional piece on battery management side that, it may or may not be fully developed for folks.
all right.
So I'll skip ahead. Let me see here. Yeah, other applications, just looking at drones or um, uh, aviation batteries. We've got a couple other proposals out where we are patiently waiting to hear back. Basically looking at uh, uh, understanding how batteries are already performing in the field for a couple different defense applications and seeing what we can to triage these batteries and instead of having them get thrown out after X number of years, maybe we can say, okay, this is still a good battery. You can still use it for another. You can conceivably use it for another X number of days or months or years before you want to replace it. So different things of that nature that we're looking at. These are some of our, I guess don't worry about the details here, but it's a quad chart for an OSIF proposal looking at aviation batteries, for example. I'll skip ahead to some of our case studies. So step one would be this eVTOL battery pack modeling. Basically, the idea here is take the data coming off of electric aircraft battery packs and use that voltage information to figure out which cells are going to be the weakest in the pack. So that's kind of circling in, going back to that previous figure, we're circling in on the weak cell identification. This is a patent pending method that came out of our SBIR. Basic idea is you give us the input data. This is in that upper left corner is the voltage traces for 196 different cells. We do the feature engineering to figure out, okay, there's, which of these cells are the outliers that we need to worry about. And we can filter out those outliers to say, okay, these are the weakest cells in this battery pack. These are the ones that you really need to watch out for as far as, the weakest cells are the ones that are going to have the biggest impact on the overall performance of the pack. So whenever that, whenever those weakest cells hit their minimum voltage, oh, my booth keeps turning the light up. Whenever the battery pack hits that minimum voltage, that's when you're going to run out of juice. So just an important consideration for electric aircraft as we work on those types of applications. So let me see. We'll go through some of the details here. I don't want to go through the whole thing, but basically, it took about halfway through an hour-long flight test to figure out which ones were the weak cells based on the previous algorithm. We were able to come up with an algorithm that uses the voltage information and teases out these weak cells with only 5 minutes worth of data instead of 30. So, like I said, this is an important consideration for battery pack health and how much energy you're going to get out of the battery pack. Maybe you can't quite see it, but what's going on here is this is a state of charge for each of those 196 different cells, and as you can see, they're kind of this is at the start of the test, this is at the middle of the test, this is at the end of the test. You can see that they're all kind of bunched together, but we still have this one that isn't balanced for some reason. So this outlier that's got the lowest state of charge is going to be the one that you want to watch out for, that has the low performance. So detrimentally dragging down the rest of the performance of the pack. So basically what we're able to do here, we've looked at a couple different battery packs. Here I've got slides for 2 different battery packs that we've looked at. We've looked at a third now, and it seems like it's reproducible, so we're happy about that. Basic idea being, okay, here's our voltage trace for these different battery packs. They've got different S&P configurations, but it works regardless of all that stuff. We're taking the first X number of minutes worth of data, feeding that into our algorithm, and trying to figure out which ones are going to be the lowest voltage at the end of the flight. So this is an example. At the end of the flight here, we've got 100 something cells all bunched together, but we've got these 2 in light blue and blue that are the weakest of the bunch, that you would say. So just using the preliminary voltage data, we can see that some of these cells are noticeably less than the other ones. So we're just trying to figure out a good outlier detection algorithm to tease those out. And it turns out that maximum voltage, which is more or less correlated with the open circuit voltage, and then voltage integral, which is sort of a proxy for average voltage here. Those are 2 of the features that end up being most predictive for this particular application. So I'm going to skip over some of the details here, but the main idea being, we put in the data, we do feature engineering based on the open circuit voltage and average voltage, and tease out the outliers, and we're able to do that with roughly 85% accuracy at this first go around, and I'll dive into how we improve that momentarily. But with a single pack that was tested 27 times, we're able to get at least repeatability, so we're happy about that. And then with 2 different manufacturers, we were able to get 85% accuracy with both of them. That is, we have both repeatability and reproducibility, so we're happy about that part. And then we're able to, look at these categories of errors that we had for the other 15% that we were missing. Part of it is just empirical error. So 5 out of our 19 misses, what ended up happening was, we just didn't get the right result. So there's more work that we can be doing to tailor our algorithm with, as we get more data, we get better at figuring out which ones are the outliers. So this is sometimes you just miss. A couple other categories would be, some of them we've got some data logging issues. So to your previous point, Eugene, we don't do anything with the sensors ourselves. We're just taking the data as it comes from our various partners. So it's obviously garbage in, garbage out. If the data is wonky for some reason, then that's going to throw off our calculations. So that's a potential hazard. And then a third category was where there wasn't even a weak cell to begin with. So in this particular application, there's only a 12 millivolt difference between the highest and lowest cell in this 196 set of 196 cells. So in this third category, we're basically looking at how can we add some missing logic to say, okay, if are there any weak cells to detect at all? And then if not, then we can just skip over this part. Um, so if we have if we have the error handling for the hardware errors and error handling for for screening out if there's no weak cells at all, then that boosts us up to 95% accuracy. There's only a minority of these 5% minority of these that we're missing that we're looking at getting better as we get more data, but we're reasonably happy with that result for starters. So like I said, we looked at these voltage features. We looked at temperature and resistance, but they did not end up being as informative as we thought. But yeah, we're at least happy to say that just looking at these features from the voltage data, that gives you a pretty good amount of information for making these forecasts ahead of time. So I guess quick recap there. Simple voltage features are useful for identifying these weak cells, predicting which cells at the end of the flight are going to be weak. We can use the voltage features from the beginning of the flight test to go and find that we ended up being 6 times faster than the previous status quo, 5 minutes versus 30. We could even optimize that further if we wanted to. We just haven't necessarily. We could probably get down to 30 minutes or 30 seconds or a minute, or we just haven't optimized for minimum time just yet. And yeah, we can get up to 95% accuracy based on the data we've got so far. And as we get more data, we can keep improving the algorithm in that particular application. So this is a patent that we've patent pending. We submitted that as of a year ago and waiting patiently to hear back on that. But yeah, I've got some electric aircraft companies that we've worked with that are excited about that particular offering of ours. Let me see here. Eugene, how are we doing for time?
You're still good. You got about 15 minutes.
Oh, okay. Yeah. So sure. Well, I'll just keep on trucking then. Another case study of ours would be from our first NSF SBIR back in 2020. This is one of the projects that got us going down the data analytics route to begin with. Here we were looking at just as a proof of concept cell lifetime forecasting. So the idea here being, excuse me, there's some famous papers from Nature that have shown that data from the voltage profiles of these battery tests is highly predictive of cell lifetime for LFP in particular. And what we were able to do is get some additional data from Sandia National Lab and a couple other sources and look at different chemistries and different load profiles. So we're basically able to expand that result to additional chemistries and temperatures and operating conditions. Basically, what we found is that the same model, the weights might be different, but the model more or less stays the same. And we believe the reason for this is that it's got the same failure mode for each of these chemistries. NCA, that's nickel, cobalt, aluminum. NMC, nickel, manganese, cobalt. LFP is lithium iron phosphate. These are 3 of the most common cathodes for batteries today. What we were able to find is that since the anode side is where the main failure mode is, that being SEI growth on the anode side, on the graphite anode, that was the features that have been engineered for this particular application are indicative of and correlate with SEI growth on the anode side. So this model we've been able to extend that to these different use cases and conditions, and we're able to get within 10% error using only 40 cycles worth of data. That improved upon the previous result they're looking at 100 cycles as their state-of-the-art um, uh, result from that particular Nature paper they reference. Uh, we've been able to get that down to about 6% error after n number of cycles. But yeah, basically we're looking at the 50 to 60% reduction in testing time if you want to go from 100 down to 40 or 50, or even much more than that if you implement this at during vendor selection or product development, QA, QC, those types of applications. If you're previously, if you're currently testing the battery for weeks or months, we can help you, do those same types of tests just a lot faster and get you the result, in days instead of weeks, using our methods. So that's another project that we're uh, uh, pretty pleased with our results there as well. Another one I'll go into. This one would be monitoring state of health using differential capacity analysis. This is another one where you're using features from the electrochemical data and using that to correlate to state of health. So this is another project that came out of our Air Force SBIR. So if you're not a battery scientist, incremental capacity analysis, this is a technique where um, you can basically take the derivative of your voltage trace, and that is going to resolve different peaks corresponding to the electrochemical reactions and phase transitions taking place inside the battery. So these peaks, they are going to evolve over time as the cycling. They're basically going to, the intensity and position is going to change with time as the internal resistance of the battery changes, and as you lose active lithium in the battery. Those types of different side reactions are consuming your active material, and you can basically use this as a way, as a quick and dirty estimate of the state of health, using just a quick linear regression. So well, the idea here being you take the charge data, you filter these incremental capacity analysis curves. So in green, we've got cycle 5 at the beginning of life. In blue, we have cycle 900 at the end of the life. And that you can see the curves are changing over time. The main feature of interest is that wherever that peak occurs, we take a voltage interval around that and measure the capacity around these peaks. So the idea here being cycle 5, you've got about 500 milliamp hours worth of capacity. By cycle 900, that's degraded down to less than 300. So in this case, about a 42% drop off between cycle 5 to cycle 900. So in general, you stop using the battery long before then, probably, but just for proof of concept, that's the idea here. And what you can do is you can just put together a simple linear fit, and it's a pretty good, quick and dirty way to estimate state of health. That capacity measurement, that regional capacity measurement, ends up being linearly proportional to state of health. So this is a way to go ahead and instead of building a much more complicated state of health estimator, this is a way that you can easily integrate this into the charging portion of whatever you're doing with that battery. So for example, here's in the blue highlighted, that's the operational data from an electric bus. So the bus is going to be doing whatever the bus is going to be doing, starting and stopping and driving through the city, versus you're going to have relatively consistent charging data on the relatively consistent charging data when you charge it back up again. So because you have that consistency, that is a good data set for us to use as input for that state of health model. So another thing that we're excited about for some of our stationary or light mobility, or anywhere where you've got relatively consistent charging profiles, is a good use for this type of method here. So we're kind of reaching the end of the things I was going to talk about here. Just to kind of wrap things up, we're like I said, we're a battery analytics startup. We're still finding our way in the world, but we've been looking at different things pertaining to aerospace and defense applications, helping the manufacturers of drones or robotics or electric aircraft get the most out of their different battery systems. We'll take your live and or historical data to develop a solution that solves whatever problem you have personally with whether that's reducing the cost of maintenance or making sure that a battery is always ready to go for whatever that next mission is. And yeah, to date, it's been mostly my most useful skill from grad school has been writing proposals. So we've been very happy to receive support from the SBIR program through both AFWorks as well as the National Science Foundation, and then a couple other irons in the fire that we'll hopefully be able to talk about in the near term as well. But yeah, just eVTOL, stationary storage, just about anywhere where you've got a battery where you care about long-term health and performance. We are more than happy to work with new partners on integrating our analytics into your offering to help you streamline your operations and maintenance. So with that, I think I'll stop here, and I guess there might not be any more questions, but if anybody's got anything else, I'm happy to field them here.
Do you have you worked at all with the healthcare industry?
Healthcare. We've not done healthcare yet. Is there a specific application you're thinking of there?
Well, a lot of the machines, instruments that are used now operate on batteries. They're not necessarily plugged in, and so I didn't know if you had looked into that.
We haven't. If there's, yeah, more than happy to if there's a particular fit there, but as of today, have not done a specific project there.
And then, so your software that you've developed and the algorithms, the analytics that you do, would any of that be applicable to another industry or would there be any other applications besides batteries? That just a few tweaks might be able to accomplish.
Yeah, I guess, my background is as a, materials electrochemist. So batteries has been what I've spent a lot of cycles thinking about, historically. It could be other electrochemical devices, capacitors or fuel cells or, flow batteries, maybe semiconductors, that type of thing. We haven't specifically looked at anything outside of batteries, but, it could be applicable to, there are certain other electrochemical types of systems that it could be applicable to.
So like would maybe RFID or IoT applications?
Yeah, potentially. It'd be a bit further out from our core competency, but still, roughly in our wheelhouse of things that, we could go and develop solutions for.
Yeah, no, exactly. I'm just trying to get a handle on where it would work, and and if anybody wants to pay to modify it. I mean, it's just like a lot of the AI stuff can be transferred from one application to another with just a few modifications, so you're not having to reinvent the wheel.
Right, right.
Working with somebody and saying, this is what we need and this is what you have, and how do we get those two to produce the result that we're looking for.
Right.
All right. Well, thank you. Thank you for your time. And
thank you.
I'll be following up after this. There'll be more people that are watching this after the fact. This is an R&D incubator platform. So most of the people that are on here from Polyplexus that have been on Polyplexus for a while, they're used to an 8-week incubator, not a 45-minute session. So, so there's a lot of people that'll come in after.
Sounds good. Well, thank you.
All right. Take care. I will be in touch. All right. So next up, we have Fernando.
Yeah.
Okay, so you're up on the screen. So Fernando's going to talk about liquefaction and where his technology and his solution applies to. So you're looking at both metals and separating out uranium.
Oops.
Fernando?
Right. Yeah.
Okay.
I'm ready to
All right.
go.
Okay, I'll turn it over to you.
Thanks. Well, good afternoon, good morning, wherever you are. My name is Fernando Vaz. I'm a founder of Smart Dry. I'm a biologist with a PhD in England in biotechnology. And my interest in mining is due to the environmental impacts of the mining sector. About 2.5 years ago, Vale, the iron ore giant from Brazil, launched a challenge to dewater iron ore on pre-embarkation of ships. And I submitted a proposal. I got some money from them to develop the technology. And this led to the development of a new dewatering solution. And during the dewatering solution experiments, I noticed that ultrafine black grains accumulated at the bottom of the dewatering equipment. And that puzzled me. I went after an explanation, and the explanation came from a Japanese researcher that published a paper on how the grains move in saturated soil during the cold earthquake. So for my amusement and completely unbelievable, grains do move during liquefaction effects. And if they do move, you can do mineral separation. And with that, a series of applicability opens up in terms of opportunities. So we are hard tech in Brazil, which is extremely challenging because investors in Brazil don't see hard techs, don't understand it. They only see digital and things like that. The leachable market is immense, right? All these metals are leachable, and iron is also bioleachable if you want to extract from tailings and things like that. So in terms of value, we only lose to crude oil, right? The sum of the leachable metals are over $1 trillion per year in value, right? So what is leaching? Well, leaching has two main areas, okay? One is the chemical, which is for each metal or has a kind of process, a recipe, if you like, of chemical solutions, process and things that will leach or extract the metal from the source. And then there is the mechanical side of the process, which basically you see three kinds of different solutions: tank, heap, and in situ. Heap and in situ are what I call mechanical, almost non-existent. It's very passive process. In heap, you simply drop the lixiviant on top of the pile and it percolates down. In situ, you have one tube that injects the solution, then migrates, and then the other tube takes out. So these two are very passive systems. The tank is a place where you put the material with the lixiviant, and under agitation, you make the lixiviant dissolve the metal. The problem with this is it's very high capex and opex and can be applied only to very high quality grade material. So this is the classical heap leaching, and in terms of uranium, in the United States, it's not much use, because the United States produces uranium, 50% of its production comes from in situ leaching. But globally, in terms of uranium, this represents about 47% of the total extraction of uranium. And of course, uranium is a strategic and an energy metal, so very important. The problem with heap leaching are several. It creates puddles on top of the pile. It creates preferential drainage channels and all these kind of things. The net result is that a very low efficient process, between 50 and 80%, depending on several factors, that you can actually remove the metal. In terms of tank leaching, the percentage rises quite a bit. It can get to 95, 96% efficiency, but it's still very costly process to be done, and restricted to very high grade ores, which are becoming more and more difficult to find. If we compare inverted leaching pile and tank leaching, you can clearly see the advantages of inverted leaching over these two present technologies. But you might be asking, okay, Fernando, so what is this inverted leaching of yours? Okay, this is manganese waste or tailing, right? And in these tubes here is being injected water. It's just to exemplify what happens during inverted leaching. Here is not actually happening inverted leaching. It's just recovery of metal. But as you can see, you inject the lixiviant and apply vibrations. What happens is the lixiviant rises through the material that it's under vibration. So the grains are rubbing against one another with high energy impacts. This should increase efficiency in extraction. When you get to the point that a liquid layer is formed on the top of the material, you can take the lixiviant from here and recirculate it down, and as many times as you need it to get it fully saturated or complete extraction of the metal. So this is it. This is what this new mechanical process of leaching is all about. It's a contraflow mechanical process that has not been seen in the mining or in leaching markets. And it brings quite a lot bunch of innovation. Okay, and it can be done in one step or in two steps. One step, you take the material, mill it, put inside the equipment, and inject the lixiviant and keep recycling. Once you get it saturated, you take it out. The two steps is where you can first, using liquefaction, create a concentrated metal. You inject water first, do liquefaction, separate dirt and metal layers, and then you take only the metal layers and put in here. The importance of this is that in both one step and two steps, you get the leachable metals out in the lixiviant, and at the same time, simultaneously, all the insoluble metals are recovered because they form a layer at the bottom of the equipment. This means less acid mine drainage, less ESG impacts, environmental, social, and governance impacts, more profitable because you're not leaching, you're not getting only the leaching material, but also the insoluble metals, which is our view of the modern new mining sector. You're going to mine all that is present in your ore, not just one or two or three target metals. You're going to mine all, right? Because there are people that are willing to buy anything that you can think of. In terms of dewatering, this is the volume of all the metals we mine. It's huge, right? Of course, iron, it's by a long way the most important in terms of volume, but copper, which is only 22 million tons per year, is the metal that produces the most quantity of tailings in the world. 40% of 282 billion tons of tailings deposit around the world come from copper, right? And then after copper, iron, because of the volume you mine every year, and then in third position, gold, right? But there are 282 billion tons of tailings, and these tailings have metals in it that liquefaction can recover and can dewater. But you're going to say, Fernando, why dewater tailings that are deposited in tailing dams? Well, I can tell you that BHP and Rio Tinto in Atacama Desert are struggling with water. 75% of the mining in the world are done in areas that water stress is a problem. BHP and Rio Tinto in Chile need to get the water from the tailing dams because the world changed. Local communities are putting pressure, everybody's putting pressure, saying you have to be more efficient with your water, right? Water is first for people, and this, they are really looking for a solution there. The problem is volumes, right? They produce 30,000 tons of tailings on every single day. So they are looking for a dewatering solution. In terms of dewatering, our technology outperforms all the other mechanical solutions. In terms of the cycle, it's very fast. We can dewater a huge amount of material when compared to the other technologies. Our equipment costs much less and consumes less energy, right? Which brings altogether to a more efficient process for dewatering. And this is, dewatering in zinc tailing, right? 50% water, 50% solids. What you do is you apply vibrations, you apply vibrations for 1 minute, right? It's not being injected water, it's just that my equipment can do both things, but this is just the water that was present in the tailings, 50%. You apply vibrations for a minute, and in the end, you remove the water using a suction device or siphoning. You have this material that is dry stackable. And here you can see showing dry stackability. What this means is that there is no more free water in the intergrain spaces. This material you can put on the ground and compact it. This is what the mining industry is looking for. They are not looking for to dry tailings, because the actual drying means using thermodynamic solutions with a very high cost. No, they want to be able to put the material on the ground and compact it and make it safe. And liquefaction does it in a much better and more efficient way than the other mechanical available solutions in the market. So this is us. Our technology has a broad application. We can recover grains, metal grains from tailings that are ultra fine. We are talking to oil companies to use liquefaction to convert oil sludge into circular economy products using liquefaction effect, again, with advantage. And we can even apply this to recycling products, mining, landfills. There is a big broad of applications. Sea mining, it needs desperately, in my opinion, a dewatering solution to make it viable, the logistics of bringing the solids from the sea or offshore to land onshore to be processed. Of course, you can process offshore, but the cost of it's quite prohibitive. It's much cheaper to bring the solids and process everything on land. So this is our technology. Our business model is based on manufacturing the equipment and selling, or hardware as a service. But our exponential growth will come from the technological fee that we're going to charge, because our equipment costs much less, produce much more, so we can charge a tech fee that will increase the amount of revenue every time we install a new equipment without increasing the cost for running it. Three people will run the financial market, the financial sector, charging, issuing, charging lips. So this is us. In terms of team, is myself, and I have two potential co-founders in the United States, and I have a vesting contract with them. But we are looking for investors and grants, right? Here in Brazil, I also looking for grants to develop pilot plants. And yesterday I got a great news that I'm gonna do a POC project in Peru with a mining company that it mines zinc in Peru, right? So this is us. This is our technology, and I can answer any questions that you may have.
All right, so Fernando, is it scalable, and to what size? I mean, can you go down in scale, up in scale?
Yes. This Peruvian process, for you to have an idea, they have a waste that is almost pure copper. It's 60% copper. It comes from the metallurgy process of the zinc mining. And they have only 40 tons per day. The problem is this material has a density of 6.3 grams per cubic centimeter. So the thing is so dense that if you try to use present mechanical dewatering solutions, it doesn't work, because it settles even before a press filter or disc filter can act, or centrifuge for that matter, in dewatering. So the equipment can go from, let's say, 2 tons per batch up to 100 tons per batch, right? It's fully desirable, and you can have any kind of size in the equipment. For both inverted leaching, recovery, and dewatering, it's fully customizable to the client operation size.
Okay, the water. So once you go through the liquefaction process and you've added the chemicals, I guess there are chemicals that go into this to help to condense the material. Is that correct?
Not
Or
really.
just water. Okay.
If you're talking about dewatering, I take the material as it comes out of your process and put inside my equipment, and I separate the liquid from the solids via liquefaction. The water will come out with some solids in it, okay, very small amount. It depends on the characteristics of material we are dewatering, but normally very small amounts. Because there is no filtering device involved, right? It's just vibrations and liquefaction effect taking place. So the water can be either passed to a sedimentation pond and then a filtration system to be reused in the process, or even treated to return to nature, depending. Right. Treatment, the use of it is somebody else's solution. right? We at the present, we are not entering this water treatment phase.
All right, so it's not like trying to pull gold plating off of metals or anything like that, where you need a chemical to actually separate that bond.
No.
You're just using water.
No. In liquefaction, what makes the separation is the difference in density and the tendency of the grain to stay inertia, right? To stay to stay stopped during vibrations. That is, the heavier, the denser the grain, it has more an inertia to stay to stay stopped. And the lighter, it has less. So that's what causes the actual mineral separation of the process. In the inverted leaching, then you're going to use a lixiviant, right? That it's normally either a strong acid or a strong alkaline solution. And this is a chemical process that we need experts from it to do it. That's one thing that I'm doing here right in Brazil, is applying for grant to be able to hire a chemical engineer expert in leaching to join the team and develop this for a very particular opportunity here in Brazil with a kaolin tailings that has a higher concentration of niobium, tantalum, and two other metals, strategic metals. The people been mining kaolin in Brazil for over 60 years and throwing away the metal, which is much more valuable than the kaolin itself, simply because they don't have the technology and they don't have the knowledge to extract the metals. And with inverted leaching, we really think we can do it in a more profitable way, because the amount of lixiviant that is needed is much less. In tank leaching, for instance, or pile leaching, you're talking about 2, 3, maybe 4 times in terms of volume per mass. In inverted leaching, we are talking about 25% of the mass in volume. So it's a quarter of the mass in terms of volume of lixiviant. And this drastic reduction in the volume of the lixiviant impacts costs upstream when it comes to the actual precipitation of metals from the lixiviant solution, right?
So is that solution, is that hazardous, or can that be neutralized?
Yes, it can be neutralized.
Process?
Yes, it can be neutralized. In our technology, we intend to do is this. We will inject the lixiviant to extract the metals. Then we're going to do a washing step that we're going to inject water to remove the last lixiviant that is still there. And after that, we're going to do what we call a neutralization step. So for instance, if the lixiviant is a strong acid like sulfuric acid, we're going to inject alkaline product like lime or something like that, that will neutralize the pH and bring the pH around to 7. So whatever tailings are left will be pH neutral or close to neutral. And this will allow us to use this material in mine closure, recovery area, this kind of things. And remember, we are also extracting the insoluble metals in the same process, meaning that we are reducing drastically the occurrence of acid mine drainage from this material. It's a very interesting new technology.
So now, what about
Sorry, it cut. What about what?
issues? And then
I didn't.
could you clean up an area? Environmental applications? Can you hear me?
Yes, We can.
Okay, so
We
yeah,
are,
'cause I was thinking if you had like a diesel spill on land or something like that, would you be able to
yes.
recover the diesel from it and produce a a dirt or a fill that was
Diesel
non-hazardous?
free. Yeah, we can. Because um, all we need to do is, let's take this example, the diesel, right? Diesel doesn't mix with the water. So what we have to do is put the material, the contaminated material inside the equipment, inject water at the bottom, vibrates, the water will rise, passing through the material and forcing the diesel up, right? Removing it from the grains and everything. And then you're gonna have a diesel layer on the very top, a water layer, and solids. And we can recirculate the water as many times as needed until we get total removal of the diesel from the soil. The other thing that can be done also in the US, there are a Manhattan Project legacy with uranium and other radioactive waste in several areas in the United States. This can be used for it also to recover and eliminate the radioactive material from either soil or tailings, waste, anything. It's possible.
All right, so when you're talking about doing it on a large scale, where you're talking about several hundred tons,
Mm-hmm. Uh,
um, does it matter that there are rocks, stones, boulders, other things, you know, tree branches,
okay.
whatever?
It doesn't matter if you're trying to decontaminate it like the diesel, right? Then it doesn't matter. But in my opinion, if you got if you're gonna have to do this, you want to be sure that there is no other metals there also, because it's very common to have, right?
Right,
And
right, yeah, a rusty
since,
barrel.
yeah, since we're gonna do the thing that we also separate the metals, right? We pay attention to this. But in terms of metal separation, yes, grain size distribution is a critical factor. Then if you have rock boulders and those kind of things, it doesn't work. Uh, but if you're trying to remove a contaminant only, then it doesn't matter. The grain size distribution is just a mechanical process that will force the contaminant upwards. Of course, depending on the characteristics of the contaminant. Diesel, it's quite easy. But I can, my knowledge of chemicals spills are quite limited. But imagine that you have a material that it's not water soluble or will not, for some reason, it's not lighter than water. Then we're gonna be in trouble trying to remove it. If it is like diesel, that it has a lower density than water itself, no problem. If not, I'm gonna have to ask for a chemical engineer saying, okay, if not water, what is the solution that I can inject here to remove this contaminant by either dissolving it or forcing it to rise as whatever liquid I'm injecting at the basis and liquefaction will force it go up, passing through the material, you see. Uh, it's, how can I say, it's a mechanical solution for a very broad applications. That's
All
the
right.
beauty of it.
Okay, so now on the metal separation,
Yeah.
do you take it beyond the conglomeration of metals? You know, so maybe what you end up with is like 80% iron, 20% copper, 2% gold, whatever. Do you then separate those, or is that left to someone else?
Well, if I have the capital, I'll do the separation myself.
Okay.
As simple as that, right? But hydrometallurgical or pyrometallurgical process are capital intensive, right? Of course, depending, I can give you a classical example. There are about 20,000 sites in the United States from the gold rush era. These sites are contaminated heavily with mercury, but they also have very good levels of gold in it. The problem is the gold companies want to mine it. Local communities say, hey, you're not going to mine the gold and leave behind the mercury. You're going to have to remove the mercury to mine the gold. And that's where the problem starts, because there was no technology that could do both. Either you recover the gold with carbon in leaching or any kind of process, but the mercury was left behind. With this technology, we can recover gold and mercury and iron and aluminum. It is present in the material, you see, and clean the process, in the process cleaning. So the actual dirt that we're going to return is going to be clean of mercury, gold, metals, and things like that.
All right.
And there are 20,000 of those sites in the United States.
Yeah.
It's
No,
amazing.
I can imagine, and I can see.
Yeah, in California, for instance, the water, the mercury in the water level is 3 times higher than any other place in the United States. Because if you put the EPA level in California, you cannot drink water in California. You cannot use water in California. Such is the level of mercury contamination in the Sierra Nevada and all those areas that were heavily gold mined in the 19th century, the gold rush, right? And left behind tons and tons and tons of mercury. It's quite shocking, but it's true.
So then you can actually extract these from water? Is that what you're saying?
From the material, from the tailings that are left behind. Because in the 19th century, what you did was you take the material hydraulically. Most of the mines were hydraulic mine, right? So then you took the material that it comes out like a paste, passed through vibration screens and things like that. So you get the nuggets and small grains, but the ultrafine grains of gold escape, right? And then you get a concentrated, and then you add mercury to it to do amalgamation, and then you take the amalgam, burn it, and then you recover the gold. But during this process, also mercury escapes and end up in the tailings. So there are some places in the United States where you find between 0.6 to 1.5 grams of gold per ton. But the problem is you also find 0.6 to 0.3 grams of mercury, which is a horrendous amount of mercury. And of course, there are iron and aluminum also in this material. But when people mine gold, if you say to them, "Oh, there is iron in it," and the guy say, "Yeah, but iron is $100 per ton. Gold is $60,000 per ton, per kilo, $60 million per ton." They don't look at. The problem is my technology. You get it both at the same time without having to do anything more. So I am
reap
the one that
all the benefits of it.
Exactly. Why not?
Yeah. No, that makes sense to me.
Yeah. There are some surprises. Okay, like I just in December I did a test with manganese. The first test I did with manganese was last December. And manganese has a very high density, much higher than iron. So I was expecting a quite straightforward mineral separation. I said, well, this high density is going to be beautiful. The moment I start the first step, I look at the equipment, I said, there is something strange going on here. Because the water was black, right? I could see that there was a lot of manganese in the water. And I say, what's going on here? Anyway, the test showed that about between 22 and 25% of the water has manganese, between 25 and 22% was manganese. And this puzzled me. I said, what on earth is happening here? And the answer is manganese oxide is a dipole molecule. And because it's a dipole molecule, it forms a link with the water, which is also a dipole molecule. So this very weak link for ultra fine grains is enough for the water to drag these grains. And you say, oh, Fernando, you're going to lose 25% of the manganese. No, we're going to have a new product, because manganese ultra fine spheres is what the EV battery needs for. You need the manganese in battery, you want the smallest spherical manganese possible. And this material coming with the water, coming out with the water, is perfect for it. I'm about to do a calcination test on it and see if we can recover like 1 micron, 2 microns spherical manganese material. If we get that, we're going to send samples to the EV battery manufacturers and say, look, we have a new method of producing this. Would this be interested to you? Right. Of course, there is a cleaning process involved, but we figured this out already, how to do it. We're going to use a high density grade column to do that, because the dirt is basic silica and clay, so very light, and the manganese is very dense. So you put in a high density column and it's going to separate quite easily. But my technology allows us to recover this ultra fine grains, 1, 2, 3 microns in diameter. And in case, for instance, of iron, I recover grains that are all smaller than 150 microns, down to 20 microns. In case of iron, they don't grind it as much. But the great opportunity there is decarbonization of steel. The industry is looking for a way to decarbonize, and the solution is hydrogen. The problem is, if you use pellet and hydrogen, you burning a lot of hydrogen to do that. I have an idea that you take the dust, the ultra-fine grains dust, inject in a new furnaces model with the hydrogen plus microwave. The microwave is going to be the thermal energy. The hydrogen will be just the reduction agent, and the chemical reaction will happen, and you end up with metal, iron, metal, water, vapor, and that's it. A full total decarbonization of steel, and a steel that has a microstructure based entirely in micrograins from tailings, smaller than 150. This is important because this increases steel resistance, right? The smallest the grain is, the smaller the grain is, the more mechanical resistance and quality the steel has. So, but you see, when I talk to the people in the steel industry, they say, yeah, but we're going to have to throw away all our furnaces and build new ones. And I say, yeah, you're going to have to. But capital is available, quite cheap capital, because the governments finally understood that if we don't decarbonize, we're going to go extinct. There is capital to do it, right? And
Right.
the projections of savings of hydrogen alone pays the interest rate you're going to pay in the you pay in the loan to build a new furnace system. So the numbers I crunch with the public information available shows it's very doable, very realistic, doable. At present level of hydrogen costs around $4 per kilogram. If it drops to two, well, then it's because presently using pellet or synthesized grains, you burn 54 kilograms of hydrogen per ton of steel produced, iron produced, right? Pig iron. Our production says that we're going to reduce this between 20 to 30%. So it's quite a reduction in the amount of hydrogen you're going to use.
Yeah, no, I definitely see applications with Department
It's
of
very,
Energy. I
yeah,
understand why you need a chemical engineer as well.
yeah,
But yeah, National
exactly.
Science Foundation, those kind of places.
Yeah, that's it. But you see, for instance, like I'm Brazilian, so I cannot apply for some kinds of grants because I'm not a US citizen or I don't hold a green card, right? I'm in the
Right,
middle of a grant submission with the DOE for nuclear fuel chain. We're gonna apply our technology to uranium extraction, right? From ores, tailings, and even contaminated soil with radioactive material, right? But we had to do a kind of a business engineering first. My two founders in the United States have working permits. They are not Americans, but they have working permits. So the DOE say, okay, if they hold 51% of the company, yes, you can apply.
yep,
And then we did this. We said, okay, no problem. We have an understanding with us. And let's see if the DOE likes our idea for nuclear fuel. But it has to go to others. It's section 58, subtopic others, because it's
right,
so off the curve, it's something so new, right? That they didn't think of it. The person in charge of the program said, use the other subtopic because we, but she actually said, please, it's very good for phase one. $300,000, $200,000, we can do a lab equipment and run the tests with uranium ore, tailings, and contaminated soil, and prove the technology works. And if
right.
we do that, then phase two is $1.1 million. Then we are cooking.
Right, I will have to talk more after this,
Oh,
because
my
yeah,
pleasure.
definitely know people that are going to be interested. I got a project idea that I want to talk to you about too. So
My
we'll
pleasure.
definitely, I'll be following up anyway. So we'll follow up on those.
Great.
All right. Well, thank you for being here. Do you
Thanks.
have anything else in closing that you wanted to say?
No, not really. If
Oh,
anyone doesn't have any questions, I'm okay.
okay.
I have Eugene has my contacts and everything. He knows he can share with everyone that is interested in talking to me. And we are developing opportunities in Brazil, in Latin America, but we also States because we see huge mining, right? There are a lot of tailings in the United States with cobalt, nickel, zinc, you name it, iron and aluminum everywhere. But here in Brazil also, and the beauty of mining tailings is that the cost, the very expensive costs, are already done. You already blasted, crush, mill it, transport it. The thing is stored either in a tailing dam or in a tailing deposit facility. All we have to do is dig it out, put inside my equipment or our equipment, liquefaction equipment, and do whatever we want. If it's leachable metals, we're going to do inverted leaching. If it is insoluble metals, we're going to do mineral separation or recovery of the fine grains, and so forth. And there are thousands of tailing deposits that are left. The company went bust. EPA has a problem with it. DOE has a problem with it. DOD has a problem with it.
Yeah, no, definitely.
So we imagine we can go to EPA and say, we're going to clean, we're going to mine, and we're going to solve your environmental problem in one operation. So
right.
EPA pays us to clean, we get the metals, and everybody's happy.
There you go.
It's,
that works.
Huge potential in the United States. Huge.
Yeah, no, I can understand for sure.
And
so,
the environmental authorizations are either in place or once were issued. So if you get to EPA and say, look, we're going to clean this, are you going to make fuss towards issuing us the permissions? I don't think they will. They will love it. Right.
So have you developed any white papers for this that you could share and we can post?
Yes, I do.
Okay.
I have some. It's in the cloud. I can send it over.
Yeah, if you can share those with me, and I'll make sure that they get posted.
Sure, no problem. We'll do.
All right.
I just need an email. Okay, pleasure.
All right, take care.
Same.
All right. There's a lot of great ideas and a lot of great technologies out there. A lot of great applications for what we presented today. So please, if share your thoughts. If you view this post today or post live, and put your comments in the comments. We're looking for ideas and applications that you see. And Fernando is also looking for a chemical engineer. So if there's a university out there that has interest in working, I'm sure that Fernando would have interest in talking with you. So thank you all again. And that wraps it up for the second session of the Innovation Ecosystem Collaboration Forum. See you next week. Bye.
Thanks a lot, Eugene, for the opportunity. Yes. And thanks everybody for listening. Okay.
Okay, Adish.
Bye.
All right.